Thank you, Fiza, for presentation. Let's applause again. And meanwhile, I invite the fifth presentation for today from University of Antwerp and IMEC. And this is presented by Nabil Nasser Bahad. So please introduce the topic and go ahead.
Hello, everyone. My name is Nabil. I'm a PhD researcher at University of Antwerp. So today I'm going to talk about GAN Augmented millimeter wave CSI for improved pose classification. So some of the slides may overlap with the presentation yesterday from my supervisor, Jeroen van Meij. So I will try to quickly go over through these slides. So, extended reality applications have become increasingly popular, ranging from gaming at home to immersive guided tours and to entire theme parks based on virtual reality. I assume most of you had a VR or AR experience in your life. Then you can probably raise your hands very quickly just to know if you had, so very few of you have VR or AR experience in your life. So let me tell you, then the experience is not fully immersive. With a clunky headset that's often bulky and attached to the wire, and clunky controllers you need to hold in order to interact with the virtual content. Well, the goal of my research is to improve the immersiveness of XR experiences by developing an integrated wireless communication and sensing solution that not only allows users to stream content wirelessly to the head-mounted display, but also allows to use those signals to derive poses, gestures of the users, enabling a radically new way of controlling your virtual self. Well, as you can see, the wired cable used to deliver content to the head-mounted display limits the immersion of the user and mobility, and there is a chance of getting tripped down. So we consider a scenario wherein wireless technology can be used to deliver this content wirelessly to the head-mounted display, and also same signals can be used to derive poses or to enable device-free interactivity in XR scenarios. Well, the wireless technology that can enable this application, we consider millimeter waves as a potential candidate. Thanks to its high bandwidth, we can achieve data rates of several gigabits per second. And also, high bandwidth means and massive MIMO at millimeter wave frequencies leads to improved sensing resolution. So why not to use millimeter wave signals for joint communication and sensing for extended reality applications? Well, coming back to the topic, pose estimation in extended reality environment is done with some sort of complex sensor fusion between cameras mounted on the head-mounted display and handheld controllers that are used to interact with the virtual content. As this turns out, the overall system becomes very complex and bulky and also difficult to scale. Moreover, the handheld controllers are unintuitive to many users. So how can we improve the immersiveness in such cases? So we can consider ESAC signals, especially at the millimeter wave frequencies. So this is with commercial off-the-shelf Wi-Fi devices. So we basically place a user, extended reality user, in between the millimeter wave devices and basically let the user to interact with the XR content, in this case, performing a set of poses. And then at the same time, we can collect signal information such as CSI from the millimeter wave signal and feed it to the deep learning based methodology to predict pose classification, so basically which pose was performed, or we can go a bit beyond further to estimate full body pose of a human's body, so as so-called the skeleton. However, in this case, the focus will be on the pose classification. Well, this works pretty well, as you saw yesterday as well. The accuracy is quite good with this base methodology for a single user. However, today I want to highlight a different challenge with Wi-Fi sensing in general, and particularly at millimeter wave frequencies. Well, data collection, as it turns out, is quite challenging part of this pipeline. So asking users to, so first you have to recruit the users, and it's a pain to recruit the users already, and to ask them to spare some time and do data collection. And then at millimeter wave frequencies, there is limited research hardware and also limited COTS functionalities lead to complexities in the data collection. So as you saw yesterday also, there were quite a few works that highlighted this challenge and tried to address it in their future work. So how can we improve the size of the data collection, or how can we reduce the effort of the data collection in such scenarios? Well, as it turns out, we can use data augmentation. So basically, data augmentation refers to introducing diverse samples of the same. For example, in case of images, you can basically think of horizontally translating the images or rotating the images, and doing so, you are introducing diverse samples to your deep learning-based methodology, and this has consequences of generalizing better. So we can learn from vision-based approaches and think of mimicking the same to our CSI data. However, one of the important considerations here you need to think is that the semantic content of the image is more or less same under different augmentations. So this is necessarily not guaranteed in case of CSI, where we have time series of amplitude measurements. So if we try to do same set of augmentations to a time series data, in this case CSI, there is no guarantee that the semantic content is preserved. And also you could validate it by computing, for example, structural similarity index, or feeding such an augmented version to a neural network and test the performance. So in both cases, both the structural similarity index and also the performance of the neural network worsens. The only augmentation that makes sense and preserves the structural similarity, you can think of using Gaussian noise, but again, it produces limited plausible data. So as in to say that these traditional augmentation methods lead to limited plausible data, and in many cases, they are not applicable to the time series CSI data. So how can we introduce more natural set of augmentations that are more broad and without requiring to go into these details of which manipulations or which operations work well? Well, as it turns out, we can use GANs for naturally introducing some augmentations in your data. So GANs have been used for a number of applications. For example, image-to-image translation, image super resolution, and image augmentation as well. Well, I quickly want you to use your phones and go to thispersondoesnotexist.com website and check. You will get a quick surprise there. It will be better if to follow what I'm saying here. So I repeat, thispersondoesnotexist.com. You can go to that website and see every time you refresh it, you will get a new face of an image or a new person that does not exist at all. So what we are doing here is that we use a generator to sample noise, and then we try to generate a fake data that is as realistic as the actual CSI sample. Well, the traditional, so the goal of the generator is basically to fool the critic or the discriminator there, sometimes called critic or discriminator. And while the goal of the discriminator is to not get fooled and catch the generator in such a game. Well, traditional GANs, the generation process is uncontrolled. So as you can see, you can get images of different faces, but there are no labels. So in order to do control generation, so basically what you want to get is, in this case, CSI, synthetic CSI corresponding to different poses. So for that, you can condition the generator on the labels, and this guides the generator to which sample or which CSI corresponding to different pose it should produce. So the generator in this case does not get access to the real CSI data, but it is actually gets a feedback through the indirect training from the critic or the discriminator. Well, I will quickly go through the slide. The data set consists of 3 users performing a set of poses. You saw this slide also yesterday, so I'll quickly skip it. So how can we train this such a min-max gain? So well, you can think of this PR as a probability distribution of the real samples, and PG as probability distribution of generated samples. Well, the goal of the generator is to bring these two distributions closer together so that the discriminator does not, basically confuses itself in classifying whether the sample belongs from the real distribution or the fake distribution. Well, the goal of the discriminator is to separate the two distributions. So basically, we need a metric to quantify how similar the two distributions are. So as it turns out, we can use a standard BCE loss to train such a GAN objective. However, the problem with BCE loss is that you can see there is a plateau in the loss function, and in that case, there is the generator does not know how to improve its prediction. Well, this happens because in such a min-max game, it's always the case that the discriminator is at advantage because of its simplicity, task of simplicity. So basically, it has to only classify real image as real and fake as fake, while the generator has a much more complex task of creating a complex image from the low-dimensional noise. So to tackle this, we use an improved loss function known as Wasserstein loss, which approximates Earth movers distance. So basically, it also takes into account the horizontal distance between the two probability distributions and has a nice gradient as a function of the space or the difference between the probability distribution. So even in the case when the two distributions are apart, the generator can still get a useful feedback from the discriminator or the critic. Through this method, we can generate a fairly large synthetic data that mimics the original data. So in this case, we generate 30,000 CSI samples, so almost 30 times the size of the original data. Now the question arises, how can we validate the consistency of the generated data? So for that, we adopt a metric from a paper, how good is my GAN? So basically, you consider GAN train and GAN test scores. So GAN train refers to training your classifier on the GAN generated data and testing on the test split of the real data, and vice versa as well for the GAN test score. So basically, the two scores give you measure of how diverse your samples are and how realistic the fake samples are, how similar they are towards the in comparison to the real samples. Well, as I pointed out previously, the standard BC loss, there are some problems with this, and the GAN training does not converge. So basically, you can see the discriminator loss is 0, and the generator loss goes on increasing. So we are in a case where the two distributions are apart, and the generator does not know how to improve its output. So also we calculate a GAN train and GAN test scores in this case, and you can see they are 40 and 30%, so very low scores, meaning that the synthetic samples are not diverse enough and are not realistic approximation of the real samples. So differently with W loss, we get a more stable training, and you can see the generator loss is more bounded, and the GAN training converges. And in this case, we get a very high accuracy as far as the synthetic data is concerned. So these represents the GAN train and GAN test scores corresponding to 3 different users. So this suggests that the generated data is highly consistent with the original data. So as a further validation step, we actually fed these synthetic data to and concatenated it with the real training data and to see how the performance increases. And you can see we get around 3% gains in case of user 1 and user 2, around 4% gains in the accuracy with respect to the user 3. So what we suppose here is that we propose a method based on conditional GANs to generate a synthetic data that is highly consistent with the original data, and this can reduce the burden of the data collection. And as a further validation, we also see that the synthetic data actually complements the real data and improves the generalization of the model. I think I can stop here. One of the important points I would like to mention is that this approach benefits more under semi-supervised settings where we assume a limited access to the target label data. And our initial results suggest that we get around 10 to 15% gains in the accuracy under semi-supervised settings using this approach. Well, in the future, we want to leverage self-supervised learning. So basically, the idea is to use unlabeled data to learn rather than using supervised labels. So in doing so, you create more generalized features that can adapt to different tasks rather than fixing your task. Yeah, that's it all from my side. Thank you for your kind attention.
So thank you, Nabil, for the entertaining presentation, and you were very excited, moving a lot. So that's very cool. I hope the audience also enjoyed. So any question, comment?